Hello everyone. Today I am going to discuss a nice question from the GATE Mathematics 2025. Okay, and this question is asked from the functional analysis topic. Okay, here there are two spaces are given. One space is x space and another one is the y space. Okay, both are continuous function spaces, but in the x space, additional restriction is that these continuous functions are vanishing at 0 and at 1, means f of 0 is equal to 0 and also f of 1 is also equal to 0, means this space x contains all the continuous functions which vanishes at 0 and 1. Okay, but this space x is associated with this supremum norm and this space y is associated with this L2 norm. Okay, these are two different norms, and given thing is that ux is the unit ball in the space x. So ux is, what is the definition of ux? Ux is equal to it contains all the continuous functions which belongs to the space x such that the supremum norm of f, because the space x is associated with the supremum norm, less than equal to 1. Similarly uy, how can we define uy? Uy is equal to f belongs to y such that here the L2 norm of f should be less than equal to 1. Okay, these are the closed unit ball, less than equal to 1. Okay, and there are two functionals are defined. Okay, one is defined on the space x, another one is defined on the space y, and tf is defined integral from 0 to infinity f of t dt, and sf is the same, but the domain of t is the unit ball ux and the domain of s is the unit ball uy. So they are given two different notation t and f, although the definition is same but their domain is different. Okay, and in question what is asking? Question is about let us see the option s1 and the option s2, and they are asking the whether the supremum value is attained or not. Supremum value means supremum of tf mod f belongs to ux. There are so many functions in ux, whether we can find a f naught such that t of f naught modulus is equal to supremum of this, whether we can find an f naught in where ux. Similarly, whether we can find and g naught function belongs to uy such that s of g naught mod is equal to supremum of f belongs to uy sf mod, whether we can find one f naught and g naught in such a way that modulus of s g naught is equal to this supremum and modulus of t f naught is equal to this, whether we can find this. First we will focus on the s2 option. Okay, because it is easier one to find. How it is easier one? Let us verify it. In the s2 option, if one can take simply the a simple guess or very nice guess is that if one can take f is identically 1 on 0 1, this function is a continuous function, no doubt. Okay, whether the L2 this belongs to uy, this belongs to uy, because we have to check the L2 norm of f. This norm we have to calculate, then integral from 0 to 1 square dt and to the power half. Clearly this value is equal to 1, so it is less than equal to 1. So f2 norm is less than equal to 1 and f is continuous, therefore it belongs to uy. Now uy and its norm is equal to 1, but we have to check that this supremum value is equal to 1. First our target is so that the supremum value is equal to 1. How can we prove that the supremum value is less than equal to 1? But we found a function f naught, this can be written f naught. Okay, f naught which is identical equal to 1, whose L2 norm is equal to 1. Now we will show that the supreme value is bounded by 1. Supreme value, how can we show that this supreme value is bounded by 1? Let me arrange these things. Okay, means we have a celebrated function f naught which is identical equal to 1, and f naught norm is equal to f naught L2 norm is equal to 1. Now we will show that we are not focusing on TF, we are focusing on this one, second option. Okay, now we will calculate the SF mode. SF mode is equal to integral from 0 to 1 f of x dx mode. This mode can be dominated by integral from 0 to 1. We will take the modulus inside, then it will be dominated by this. Then we will apply Cauchy-Schwarz inequality 0 to 1 fx mod square dx, or you will write in notation from Cauchy-Schwarz inequality. It gives f L2 norm less than f L2 norm 1 L2 norm, and we have already proved that the function 1 multiplied this one, L2 norm of this one is equal to 1. So it gives that, but we are taking f from uy. Okay, this means L2 norm of f this means L2 norm of f less than equal to 1. So but we have proved that the function 1 has L2 norm 1, so this norm is bounded by 1 into 1 is equal to 1. Therefore the SF modulus is bounded by 1. Therefore the supremum value of this is also bounded by 1. But we have proved that the function this has L2 norm 1, so therefore this supremum value is exactly equal to 1. Okay, and we have proved that this is attained by this constant function 1. Therefore S2 is true for the function f naught which is identical equal to 1. Okay, therefore S2 is true. Okay, S2 is true means S1 is true, for S2 is false, this is false. Okay, S2 is true, S1 is false, but we are not sure about S1 is false or not. We have to check it. Let us check these things. Okay, now we will focus on the S1. Okay, let us proceed to focus on the S1. But before going to proceed S1, first we have to calculate the value for the supreme value for the S1. Means we have currently we have shown that this supreme value is equal to 1. Now we have to check what is the value supreme value of this one, whether it is also equal to 1. Let us check, because we have to calculate TF mode. Okay, but TF mode for f belongs to ux. Okay, then it is the nothing but integral from 0 to 1 f of x dx mode. Okay, and this mode is less than equal to 0 to 1 f of x mod dx. But f belongs to ux means what? The supremum norm of this one is less than equal to 1. Okay, this one is less than equal to 1. Therefore fx modulus is less than equal to f of supremum norm, which is less than equal to 1. Therefore fx mod is dominated by 1. So this can be 0 to 1 dx, and it is 1. Therefore the TF mode is less than equal to 1 for all f. Therefore the supreme value is also less than equal to 1. Now we will show that this supremum value cannot be attained. Okay, the supreme value cannot be attained, but till now it is not sure that whether this value is exactly equal to 1 or not. This is not sure till now, not sure. First we will sure it. Okay, make it sure that this value is exactly equal to 1, because less than equal to 1 does not imply that it is exactly equal to 1. First we will make it sure. Okay, first we have to prove this one, this value is exactly equal to 1. But before that we have proved that this value is supreme value is less than equal to 1. We have already proved. Let me write it star supremum of TF mode f belongs to ux is less than equal to 1. We have proved this one, but this does not guarantee that this supreme value is exactly equal to 1. Therefore first our claim is to prove this one, then we will prove that if this tf mod is equal to 1, then it is either exactly equal to 1 or exactly equal to minus 1, because if we open it, it gives tf equal to plus minus 1. If tf equal to 1, that implies that f equal to 1, and if tf equal to minus 1, it implies that f is equal to minus 1 identically. These are identical things, okay. Therefore if we can prove this one, and we prove this one, then we will take that suppose there exists a function whose value is this modulus is attained, then it gives either equal to 1 and it gives either equal to minus 1. But this f equal to 1, f equal to minus 1 does not lie on the space ux. Why? Because they are not vanishing on the boundary, because ux function require that f of 0 equal to 0 and f of 1 is also equal to 0, but these functions, these continuous functions have no such property. Therefore the operator t cannot attend the function f such that tf is equal to 1. This can be verified. So to verify the option 2, we need to show these things. First we will show this thing and then we will show this thing, okay. To show this one, we will consider a sequence of a continuous function. We consider the following sequence of continuous function. This one, f epsilon x is equal to x over epsilon for x belongs to 0 to epsilon, and 1 from epsilon to 1 minus epsilon. Then we will take 1 minus x to 1 minus x upon epsilon for x belongs to 1 minus epsilon to 1, okay, for x belongs to, or here you can write x belongs to, okay. How you are guessing this function? This is these functions are nothing but the approximation of our function. We are approximating the function 1, but this function does not lie in ux, because this function is not vanishing at the boundary 0 and 1, but we are constructing in such a way that it is approaching to the function identically 1, but it also gives the 0 at the boundary. So we are taking this type of function. We are taking this linear functions, and in this region it is exactly equal to 1, and slowly it is vanishing to 1. Means f epsilon is approaching to the function identically 1, but it has nice property that f epsilon of 0 is equal to 0, and it is also giving 0 at the point 1, okay. If and clearly this is a continuous function, okay. These are continuous functions, and it has nice property that f epsilon 0 is equal to 0 and epsilon 1 is equal to 1, okay. F of epsilon 1 equal to 1 and f epsilon are continuous functions, okay. Now we will calculate tf of epsilon, okay. Means f of epsilons are lying in the space ux. Because clearly these functions are ux, because one doubt is whether to say f of epsilon lie in ux, but one have to check that f of epsilon mod is f of epsilon mod okay, supremum of f of epsilon infinite num, because all these functions are less than equal to 1, so there is no doubt, and it also implies that f epsilon supremum norm is less than equal to 1, because it is vanishing on the boundary and it is continuous, but we have to check these things whether these supreme value is less than equal to 1, because from the graph it is clear that these functions are not exceeding the line, this line y equal to 1, okay. So therefore this supreme value is less than equal to 1, so therefore f of epsilon lie in this ux. Now we are calculating t of epsilon, okay. If we calculate this by using integration, then we will prove that its value is equal to 1 minus epsilon. So when epsilon goes to 0, it is approaching to 1, so therefore the supremum value of this quantity is equal to 1, but this quantity already lies in this space. So in this quantity, because the epsilon functions are lying already in the ux, so therefore this value is clearly greater than equal to this value, okay. So therefore it is greater than equal to 1, therefore supreme value is greater than equal to 1. But in the previous section, in the previous part, means here we have proved that this in star we have proved that it is less than equal to 1, and in the double star here we proved that it is greater than equal to 1. Therefore the supreme value is exactly equal to 1. Now we have proved this one. Now we will check that whether this supreme value can be attained by some continuous functions in the space ux, whether or not. For some this one we prove that this cannot be attained, because if it is attained, suppose there is some function whose modulus is 1, then we will prove that it is identical equal to 1. F can be identical equal to 1, or f can be identical equal to minus 1. But these functions does not lie in the space ux, so therefore it is a contradiction. Initially we are taking f belongs to ux, but these functions are does not lie, therefore it will contradict. Now our next task is to show that if this happens, okay, then f is equal to 1, identical equal to 1, or f is equal to minus 1, either this one or this one, minus 1. Okay, so we will start that tf mod equal to 1 for some f belongs to ux. This implies that this one, because it is a number, if x mod is equal to 1, it implies x equal to plus minus 1. Okay, it implies x equal to plus minus 1. Okay, so we are applying this thing here, we get this step. Okay, we consider two cases separately. Suppose if tf equal to 1 and f belongs to here, f belongs to ux. Okay, this implies tf, that definition of tf is this one, and f belongs to ux means supremum value of f is less than equal to 1, f is a continuous function. If we will take this integral on the right hand side, it gives this one. Okay, and 1 can be written as integration from 0 to 1 dt, and then it can be converted to this step. Okay, but in this step the nice thing is that 1 minus ft, 1 is a continuous function, ft is a continuous function, so 1 minus ft is a continuous function, no doubt, and 1 minus ft is less than 1 minus ft is greater than equal to 0. Why? Because ft is less than equal to 1, because the supreme value of f is less than equal to 1, therefore the function ft is bounded by 1. It implies that this quantity is a non-negative quantity, means the integral of an this is a non-negative continuous function and its integral value is 0, therefore this continuous function is exactly equal to 0 for all t belongs to 0, 1. This is the nice property of the continuous function. If the integral of a non-negative continuous function value is 0, then the integrand itself is identical equal to 0, therefore f is equal to 1. Similarly, one can prove that f is equal if this value is minus 1, then f value is identical equal to minus 1. Let us prove it. So we will open this by definition, then we will bring minus 1 to plus 1 on the left hand side, then this can be rewritten, and these things are same, this can be rewritten in this way. Okay, and here is also ft is also bounded by minus 1. Ft lies between minus 1 to 1. Okay, because this thing, therefore it is also non-negative quantity. Okay, here 1 is a positive thing, its highest negative can be minus 1, therefore 1 plus ft is a non-negative and 1 plus ft is a continuous function. If the integrand of a non-negative continuous, if the integral of a non-negative continuous function is exactly equal to 0, then the integrand itself is exactly equal to 0. It implies ft equal to minus 1 for all t, and it is identical equal to minus 1. But this function f equal to minus 1 and f equal to 1 does not lie in the space ux. Okay, therefore we cannot get a function f such that tf mod is equal to 1 on the space ux. Therefore the option S1 is false. Means we cannot we cannot get a function in ux, this one, such that it will be equal to 1 or it will attain its supremum. Therefore S1 is false and S2 is true. S1 is true, this is false. Okay, and S2 is true and S1 is false, this is true one, and both S1 and S2 are true, this is false one, neither S1, this is also false. Therefore option B is correct. Okay, I hope that you all understood it very well. Thank you everyone.